Sidereal time is the hour angle of the invisible vernal equinox point in the sky. A sidereal day is 4 minutes shorter than solar day and depends on Earth's rotation. During the upper culmination of any star, sidereal time exactly equals its right ascension. This precise measurement is essential for scientists to unlock deep secrets of our universe.
Welcome to today's lecture. We're here to undertake a rigorous examination of sidereal time, a concept that is absolutely fundamental to observational astronomy. It is, in essence, the clock of the cosmos itself.
So let's begin by outlining the structure of our discussion. We're going to start with the fundamental definition, then move to its practical measurement. From there, we'll discuss the concept of culmination, compare sidereal and solar days, and finally, we'll conclude with the key takeaways.
All right. Our first section establishes the theoretical foundation of sidereal time. To really grasp this, we have to start with a very specific, though abstract, point of reference in the sky. Let's dive in. Formally, sidereal time is defined as the hour angle of the vernal equinox point. Now, let's unpack that. Imagine the Earth at the absolute center of a vast, imaginary celestial sphere. On the surface of the sphere are all the stars. The vernal equinox is a specific, invisible point on this sphere's equator. It's the location where the sun crosses from south to north each spring.
Okay, but what does this mean for you, an observer on the ground? Well, picture your local meridian. This is an imaginary arc that stretches across the sky from due north to due south, passing directly over your head. Think of it as a fixed finish line in the sky. As the Earth rotates, that abstract point, the vernal equinox, appears to travel across the celestial sphere, just like a star would. So, the angle between your fixed meridian and the current position of that vernal equinox measured along the celestial equator is precisely the local sidereal time. And of course, this angle is constantly increasing as the Earth spins on its axis.
That all works beautifully in theory, but it presents a rather significant practical challenge. The vernal equinox is completely invisible. So, how do we actually measure sidereal time?
This is the central problem. We can't directly observe this point passing our meridian, so the solution lies in using the stars themselves as our reference markers. We use something we can see to find the position of something we can't.
We use this fundamental relationship. Sidereal time equals the right ascension of any celestial object, plus that object's current hour angle. Now, right ascension, often denoted by alpha, is like a star's permanent longitude on the celestial map. And the hour angle, t, is the changing angle between your meridian and the star.
This brilliantly illustrates the geometry. The right ascension, alpha, is the fixed angular distance from the vernal equinox to the star. The hour angle, t, is the changing angle from your meridian to that same star. When you sum those two angles, their total gives you the angle from your meridian all the way back to the vernal equinox. And that, of course, is our sidereal time, s.
Now, this relationship becomes incredibly simple and useful during a key observational event, the culmination of a star. This is the moment when a star crosses your local meridian.
We distinguish between upper and lower culmination. At upper culmination, the object is on our meridian. Its hour angle, by definition, is 0. So our formula, S is equal to alpha plus t, simplifies beautifully. The local sidereal time is exactly equal to the object's right ascension. For lower culmination, 12 hours later, the hour angle is simply 12 hours.
So this is the crucial point. This provides a direct, practical method for determining sidereal time. If you observe a star with a known right ascension at the exact moment it culminates, the moment it crosses your meridian, you instantly know the local sidereal time. It's a remarkably elegant solution. Now let's address a common point of confusion: the difference between the time we use in our daily lives, solar time, and the time astronomers use for their observations.
You see, a sidereal day, the time it takes for Earth to complete one full 360-degree rotation relative to the distant stars, is approximately 4 minutes shorter than a solar day. But why? Why does this discrepancy exist?
Well, it's a result of a two-part motion. As the Earth completes one full 360-degree spin relative to the stars, it has also moved slightly along its orbit around the Sun. So to bring the Sun back to the same meridian on the next day, the Earth has to rotate a little bit further, about 1 extra degree in fact, and that additional turn takes those extra 4 minutes.
And because of this continuous drift, solar noon occurs at a progressively later sidereal time each day.
This effectively desynchronizes our daily life, which is tied to the sun, from the true rotational period of our planet as measured against the backdrop of the cosmos.
Let's conclude by synthesizing the core principles we have discussed. It's important to have these concepts clear. Remember these three critical points. First, the formula S equals alpha plus t, which links the coordinates together. Second, the special condition at culmination, where sidereal time is exactly equal to a star's right ascension. And third, that fundamental 4-minute difference between the sidereal and solar days driven by Earth's orbit.
I will leave you with a final thought to consider. If sidereal time is the true measure of our planet's rotation against the backdrop of the cosmos, what does its disconnect from our daily solar time reveal about our perspective as observers on a moving platform in a vast universe? Thank you.
Thank you, friends. Strive for understanding and become wiser. See you soon.